Hello class, today we're going to is day 2, concavity. So we're going to use the idea of rate of change that we learned last class to help us determine if something is concave up or concave down. So before we even use anything, let's talk about things being concave up or concave down. So I want to draw something that's both increasing and concave up, and I just made everything in quadrant 1, but this graph could be anywhere, any of the quadrants. Just for ease, I just made everything in quadrant 1. So something that is increasing has to go uphill and curving up, be something like this. So what can we say about its rate of change? Well, let's see, rate of change, another word for rate of change is slope. So if I drew a slope here, a slope here, and a slope here, we could say the slope is going from 1 to 2 to 3. So my rate of change, I'm going to use ROC, is both positive, those are positive numbers, and look at the trend, it's going from 1 to 2 to 3, and it's increasing. So when something is concave up, another way to describe concave up is that it has an increasing rate of change, as you can see here, because I always read everything from left to right. So now I need to draw a graph that is increasing and concave down. So it's got to be going uphill and curving down. So maybe something like this. So what can I say about its rate of change? Well, if I draw little slopes, one here, and one here, I can say the slope is equal from 3 to 2 to 1. So again, my rate of change is positive because the function is increasing, but these values 3 to 2 to 1 are decreasing in value. So another way to call concave down is a decreasing rate of change, because for something to curve down, the rate of change has to be decreasing in value. So now I need to draw a graph that is decreasing, going downhill, and is curving up or concave up. That would be something like this. So what can I say about its rate of change? Well, if I draw little slopes here, like this, I could say this slope is probably something like a -3. This slope is something like a -2, and this slope here is something like a -1. Okay, so obviously the rate of change is decreasing. Those are, is negative. Those are all negative numbers, and because it's decreasing, the slopes have to be negative, going downhill, and these values from -3 to -2 to -1, they are increasing in value. So another way to call concave up, again, is still increasing rate of change. For something to curve up, these slope values, these rate of change values, have to be increasing in value. And finally, this last graph, I need something that is decreasing, going downhill, and concave down, curving down. That would be something like this. So let's look at its rate of change. Let me draw some little slopes, one here, one here, one here. I could say maybe the slope is going downhill, -1, -2, pretty sloppy, -2, and this last one is -3. So the rate of change is negative because the function is decreasing, going downhill, and -1 to -2 to -3, it is decreasing in value. So another way to call concave down is a decreasing rate of change. Now if we look carefully at all 4 of them, I'm going to pan out a little bit, you can see, our rate of change being positive is not the same thing as our rate of change being increasing. Okay? They are two different ideas. So in the previous day, I talked about the rate of change being the most important idea in mathematics. It is really a big idea because it can really tell me a lot. First of all, it can tell me if a function is increasing, decreasing, or if it's constant. And I think you've seen this before. Maybe we called it slope, but they say it is still the same idea. If I have a rate of change that is positive, that means I have a function that is increasing. Obviously, you know, if you have a positive slope, the line was going uphill. Well, guess what? It applies it both ways. If I have a function that is increasing, that means I have a rate of change that is positive. Rate of change positive, increasing function, rate of change positive. They go hand in hand. Now, if I have a rate of change that is negative, obviously I have a function that is decreasing. But again, if I have a function that is decreasing, I have a rate of change that is negative. And again, I have three choices. I could have a positive rate of change, a negative rate of change, or I'm going to have a rate of change that is equal to 0. That means my function is constant, or what we call a horizontal line, or we're going to learn today, sometimes you're going to talk about things today that could be a local min or maximum. But again, it is implied both ways. If you have something that is a local min or local max, its rate of change is 0, or if something is a horizontal line, its rate of change or slope is 0, and so on and so forth. You've seen some of this before. This isn't too tough. But how can rate of change help me with concavity? How can I tell if something is either concave up, concave down, or neither? Okay? Well, let's talk about what we saw on the previous page. If my rate of change is increasing in value, when we saw the rate of change was going from 1 to 2 to 3, we had something that was the function is concave up. Okay, it is curving up. But it implies both ways. If something is concave up, its rate of change is increasing in value. If we have my rate of change is decreasing in value, that's because function, is concave down. But again, if something is concave down, it's because its rate of change is decreasing. We saw on the previous page, when we had things that were concave down, the rate of change went from 3 to 2 to 1. See, it's decreasing in value, trending down. And finally, I have increasing, decreasing, or constant. So if my rate of change is constant, a function has no concavity, or it is a linear function. The definition of a linear function is that its slope is a constant rate of change. And then you've seen that before. So we're going to use a graph of x cubed to look at concavity. But I can look at the graph and figure out concavity. I want to use my rate of change to figure out concavity. So I got all these points. I'm going to label all these points. Okay, so I label all my points, and I want to figure out the average rate of change. And rate of change is just slope, change in y over change in x. So I'm going to figure it out between x equals -3 and -2. So I'm trying to figure out this rate of change right here. And I do the change in y over change in x. I get my rate of change is equal to 19. And then I do it from here to here, and I plug in the numbers. I get my rate of change is equal to 7. And then I finally do it from here to here. I see my rate of change is equal to 1. So let's look at the trend of the rate of change. These numbers are all positive, so I could tell this graph is going uphill, no doubt about it. This graph is increasing. But the trend of these numbers, 19 to 7 to 1, the rate of change values are decreasing in value. That's why that part of the graph is concave down. That's what we're looking at. Now I could do the same thing over here for the next part. So my rate of change is still changing y over change in x. From 0 to 1, it's from here to here. And I can see this rate of change is equal to 1. And the next one from x equals 1 to 2, I get that rate of change is equal to 7. And then the last part, I get the rate of change from x equals 2 to 3. I get my rate of change is equal to 19. And obviously these numbers are all positive because this function is going uphill increasing. But the trend of these numbers, 1 to 7 to 19, my rate of change values are increasing because this graph is concave up. Increasing rate of change, concave up. Decreasing rate of change, concave down. And actually that's what I'm going to put on the bottom. If something is concave up, the average rate of change is increasing or trending up. And if something is concave down, the average rate of change is decreasing, or what I call trending down. So I'm going to take all these points on the graph, A through F, and I'm going to talk about the f of x value, the rate of change value, and the concavity value. I'm always going to fill in either positive, negative, or 0 for any one of these squares, and then I'm going to give a reason, a short little explanation. So f of x is just really the y value. ROC is just really the slope. And the concavity is, how is it curving? So let's do the y value for all of them. That's the easiest one. I'm going to move this up a little bit. Okay, so at point A right here, obviously this f of x value is negative, b is positive, c is barely positive, d is 0, e is positive, and f is negative. And the reason why this is a negative value at A, because it is below the x-axis. Point B is above the x-axis. This is above the x-axis. This is on the x-axis, also known as an x-intercept. This is above the x-axis. And finally, we have the f is below the x-axis. So that's all we really had to do. Figure out what's going on. And those are the easiest ones. The f of x value, the y values are easy. Now let's look at slope. I'm going to use purple. So right here, this slope, I had to draw a tangent line slope. That slope is definitely going uphill. So the rate of change at point A is positive. But what is the reason that it's positive? The reason it's positive because at that point A, the function, I'm going to call it f of x, is increasing. So it seems like my reason here, when I do my reason here, I'm kind of using f of x, the previous set of information, to figure that out. Well, the next one here, if I had to draw a tangent line, well, right there, I think that is a horizontal line. That slope or rate of change is 0. And the reason is because point B is what we call a local maximum. It's not the maximum for the whole graph, but in this little neighborhood, in this little area, it is a local max. If I draw a slope at C, you could see at point C that is going downhill. I have a negative slope. That's because my function is decreasing. Now for me to continue this, I'm going to shrink it up a little bit. At D, I have a positive slope because my function is increasing. At E, I have one of those zero slopes again, because I have another local maximum. And finally at F, I have a really steep negative slope because my function is decreasing there. Okay, so not only are we telling what we have, either a positive or negative rate of change, I'm giving a reason why. And like I said before, they all match up. Positive ROC means my function is increasing. My function is increasing. Positive ROC. Now I'm going to do concavity, how things are curving. Concavity never switches at a minimum or maximum. So point B, point E, and this point right here I'm going to put in orange, will never be the places where it switches from concave up to concave down. It's always somewhere in the middle. I'm going to draw little slashes. So maybe there it switches, and maybe right around here it switches. And if you look carefully, you can maybe see, I mean, it's not really perfect, but it's pretty darn close, that at this first orange slash, it switches from concave down to concave up, and the second orange slash, it switches from concave up to concave down. So let's talk about its concavity. We use blue. So right here, this first point at concave at point A, you could see this is all curving down. So it has negative concavity, and the reason is because the ROC is decreasing in value. So it's look like when I have a reason, pick something green. When I do a reason, it looks like I'm going to use my ROC as part of my reason here. Again, point B is a negative. My ROC is decreasing. If you want to put numbers to this, maybe the slope here is 3, maybe right here it's 1, maybe right here is 0, maybe right here it's -1. You could see in that part of the graph, those ROC values are trending down. At point C, this is where it's very special. The ROC right there, I mean the concavity right there is 0 because it's where it switches from concave down to concave up. We call that the inflection point. If you remember that from Algebra 2. Okay, I'm going to switch this up so I can see everything. Point D is on what I call the cup up part of the graph, so that's positive. That means my ROC is increasing in value. Part E is on the concave down, negative, because my ROC is decreasing in value, and even F, because it doesn't switch concavity, it still says concave down. My ROC is decreasing in value. Now I don't want you to overthink. Look, every time, I'm going to put yellow, I put a positive sign here, and look, I put the word increasing. I use a negative sign here, I put the words decreasing. Positive sign, I use the words increasing. Negative sign, I put the words decreasing. But you have to tell me what's increasing or decreasing. You just can't put down, oh, ROC is positive, increasing. You have to say the function is increasing. Or you can't do concavity is negative and just put decreasing. You have to say the ROC or the rate of change is decreasing. They go hand in hand. You know, this takes a little bit of work, but it's not really that hard once you get the hang of it. So that last page, we did a graph, and we were able to label points and tell me if the ROC was positive, negative, or 0, and if the concavity is positive, negative, or 0, depending on what's going on with the function. I'm going to do it to a table now. Now, what's missing? Well, the most important idea that I need, and if I have a table of x's and y's, or f of x, I need to figure out the rate of change, which is just change in y over change in x. So in between all these points here, between these points, I'm going to do change in y over change in x. Now I made it very easy because the whole time in this table, the change in x is just equal to 1. So it's just looking at what's going on with the change in y. So for this, between 8 and 4, it is going down by 4, negative 4. Positive and negatives do matter. This one's going down by 2, down by 1, down by 2, down by 3, down by 8. Okay? That's just figuring out the change in y over change in x. We're seeing what's going on with the table. Now it asks, is this function increasing or decreasing? Okay, and y at 2. So right around here at 2, I'm going to circle, here's my little neighborhood around x equals 2. And let's see what's going on. Well, I know this function is decreasing because I could see the y values are going down in value. But that's not really a high-level way of saying things. This function is decreasing because my ROC values is negative right there. Right? If this ROC is negative 4 and this one is negative 2, right here in the middle somewhere, it's going to be some negative number. Okay? That's a better way of saying it. This function is decreasing because it has a negative rate of change. Okay? Now it asks, is it concave up or concave down? Well, let's see. Let's see the trend of these trends of the ROC values. This goes from negative 4 to negative 2. Oh, that's trending up. So this function is concave up because ROC is increasing. It's trending up. Okay? So that's why ROC is very important. It can really explain a lot. I'm going to do the same thing again. I'm going to have to shrink it up a little bit so I can see the table and do the next couple problems. I'll do in purple. So it's saying at x equals 5. X equals 5 is right here. So when x equals 5, guess what? My function is still decreasing. Yes, I know the y values are going down because my rate of change is negative. And then I look at the trend, negative 2 to negative 3. They're not the same. It's not constant. So the function is concave down because the ROC is trending down or is decreasing in value from negative 2 to negative 3. See, I don't have to see a graph to determine if a function is increasing or decreasing or is concave up or concave down. I could just use the ROC value all by itself. And like I said on 2 pages before, these are connected together. Negative rate of change means decreasing function. Increasing rate of change means concave up. And decreasing rate of change means concave down. And again, I'm going to give this problem because this problem is not going to go away. You're probably going to see this at almost every homework assignment, almost every single quiz, probably for the next month. So you better get used to it. It's not going to go away. Rate of change is change in y over change in x, or what I call y2 minus y1 over x2 minus x1. I can see right now the x's are going to cancel on the bottom. This says plug x plus h into the function. So 3 x plus h squared plus 4 x plus h minus 2 minus parentheses the original function. Don't forget to put parentheses when you subtract the original function. All over h. Now I have to expand it. Hopefully you remember that x plus h squared is x squared plus 2xh plus h squared, right? Except there's a 3 in front. So I have to multiply all that by 3. So I can put a 3 up front here. This becomes a 6. And I'm going to have to move this a little bit. This becomes a 3h squared. Then I'm going to distribute the 4 plus 4x plus 4h minus 2. Now I have to subtract all this or make them opposite. 3x squared plus 4x. Excuse me, I didn't make it opposite. Not even paying attention. Minus 4x plus 2 all over h. And this is my favorite step. Now you got to start to cancel. Everything without an h better cancel out. If you left with something that doesn't, if you left with a term that doesn't have an h in it, you got to say to yourself, I messed up. 2 has a buddy -2, -4x has a buddy +4x, and -3x squared has a buddy 3x squared. I kind of do it in reverse. 6xh plus 3h squared plus 4h over h. We are dividing by 1h. So this 1h cancels out 1h here, cancels out 1h here, cancels out 1h here. And I get my rate of change is equal to 6x plus 3h plus 4. Again, get used to this problem. We're going to do it all year.